All right, these are our notes for Module 4, which are on functions. We're going to look at the definition, the domain and range of functions, graph of functions, operations, and inverses. So the first set is just some terminology related to functions. And our first one is a relation I don't know, it's not working. There we go. So a relation is any set of ordered pairs. And remember, our ordered pairs are in the form of x, y. So it's two numbers. So any relation is a set of ordered pairs. The domain of the set is all the first components of the ordered pairs. So it's generally our x values, but think first value. The range of the relation is the set of all second components of the ordered pairs, generally your y values. So here in this ordered pair, here's our domain, here's our range. And then our last one is a function. So a function looks at a relation, and a relation is a function if each first component corresponds to exactly one second component. And in our case, typically it's each x has exactly one y value to go to. So here we're going to look at a set of ordered pairs and give the domain, the range, and tell if it is a function or not. So for our first one, our domain, remember, is our x values. So our domain is going to be 0, 4, 3, and 10. Our range is our y values, or the second value in the ordered pairs. So it's going to be 2, 5, 7, and -1. Now, if we look at this, the definition of a function is each first component has exactly one second component. Each first component goes to one y, or each x has one y value. So if I look here and I look at the relationship, each x goes to exactly one y. So yes, this is a function. For B, when we list our domain, it's going to be our x values again. So it's going to be -3, 0, 5, and 1. For our range, we are going to do the y values. So it will be 2, -2, and then my last two y values are both 5s. So I'm only going to list it once. If it repeats, you only list it once. Now, when I look at my relationship here, to see if it's a function, -3 goes to 2, 0 goes to -2, 5 goes to 5, and 1 goes to 5. So for this one, if we look at our x values, each x value goes to exactly one y. Now, 5 and 1 go to the same y value, but that's okay. It doesn't matter if they go to the same y value. They can only go to one y value. Basically, so this, yes, this is a function. What would make this not a function is, let's say -3 was listed up there twice, and -3 went to 2, and it also went to -2. If that was the case, if there were two branches off of a domain, it would not be a function. All right, so for C, my domain is going to be -3, 0, 5, And again, 5 is listed twice, so we only have to put it down once. My range is 2, -2, and 6. And then -2 is listed twice, so I'm only going to write it once. Now, when I look at my relationship here, -3 goes to 2, 0 goes to -2, 5 goes to 6, and then 5 also goes to -2. So is this a function? If you look at our x values, 5 goes to 2 different places. Remember, each x value can only have one y value. Since this x value has 2, this is not a function. So this would be no. All right, for D, okay, here's my x, or my input, y is my output. My domain would be 95, 81, and 73. My range is A, B, B minus, and C. And they've already kind of drawn on here our relationships, and if you look at it, 95, so this input only has one output, but 81 goes to B minus and B. Since this has 2 outputs, is this a function? The correct answer would be no. It has to have only one output. All right, so now what we're going to do is they're going to give us a function and they're going to ask us to find the indicated value or simplify the expression. So what they've done here is here's our function, f of x equals 3x minus 4, and they want us to find f of 2. Really, all you do here to find f of 2 is where there's an x in your function, you plug in the numerical value they gave you in the parentheses. So we're going to plug in 2. So we're going to do 3 times 2 minus 4. 3 times 2 is 6. 6 minus 4 will give me 2. So f of 2 equals 2 in this case. We plugged it in, that's what we got. Now f of -3 we're also going to evaluate. So again, we're going to plug in our values. And the first thing we're going to do is we'll do 3 times -3 minus 4. 3 times -3 will give me a -9. -9 minus 4 is going to equal, and do plus a negative, so you get -13. So f of -3 equals -13. All right, now, for B, we have g of x equals -7x squared plus x. First, we're going to do g of 3. So we'll do -7 times 3 squared plus 3. So if you remember, order of operations, we do exponents first. So we'll get -7 times 9, because 3 squared is 9, plus 3. -7 times 9 is -63 plus 3. So our final answer is -60. All right, and next we are going to do -4. So g of -4, which means we'll do, again, -7 times -4 squared plus negative 4. So negative 4 squared is 16. So we have negative 7 times 16, because two negatives make a positive, plus negative 4. Negative 7 times 16 is negative 112, plus negative 4. So that's going to give us, for our answer, negative 116. And that's all we do there. All right, now they give us a function. We have p of x equals 4x squared plus 2. And the first one they want us to find is p of a. And again, whatever's in this set of parentheses is what you plug in for the variable in your original function. So p of a is going to be 4, and instead of x squared, we're going to do a squared plus 2. Now, because we don't know what a is, and it's not a numerical value, that's all we can do. So that problem is done. Our next one is p of b plus 1. Now this one's going to require a little bit more work because we're going to plug in, we're going to do 4, and then instead of x squared, we're going to plug in b plus 1 squared plus 2. So now we have to evaluate. And what we're going to do is, remember, we're squaring this entire expression. So it's going to be 4 times b plus 1 times b plus 1 plus 2. So we have to FOIL here. What I'm going to do to make it a little easier is I'm going to distribute the 4 to the first set of parentheses. So I'll have 4b plus 4 times b plus 1 plus 2, and then we'll FOIL. So 4b times b will give me 4b squared. 4b times 1 will be plus 4b. Then we'll do plus another 4b and plus 4 plus 2. And then we'll combine our like terms. So we will get 4b squared, that's a plus sign there, plus 8b plus 6. And because we don't have any more like terms, that is our final answer. Right here, we are looking at our vertical line test. And if you have a graph of a relation, you can see if it is a function, if it passes the vertical line test. And a relation passes the vertical line test if no vertical line can be constructed so that it intersects with the graph at more than one point. So remember, our vertical line, vertical goes straight up and down. So what you can do is take your pencil, and we read a graph from left to right. So take your pencil, lay it on the graph. In mine, obviously I can't demonstrate this quite, but you lay it on the graph and you move it from left to right. Look at the edge of your pencil. Does it touch the graph in more than one place? And here I'm just going to draw some vertical lines to show you, like if I go across here, if I look at my vertical lines, you can imagine my pencil going across. Here, my vertical lines are never going to touch the graph in more than one place. So A is a function. Okay. Now B, if I draw my vertical lines, okay, if you stop and look at 3 of these vertical lines that I've already drawn, notice it touches the graph here, it touches the graph here, it touches the graph here, it touches the graph here. On my vertical lines, because I have vertical lines that touch the graph at more than one place at a time, so 2 places, right here and right here, or on this one right here and right here, this is not a function. So no, it is not a function. All right, we have an ellipse here. Look, right there, I can draw a vertical line, touches at 2 places. So not a function. And then D is an absolute value graph. And this one's a little bit harder, but if you look, if I just sketch in some vertical lines, as I'm drawing it, it never touches a vertical line more than once at a time. So yes, this is a function. All right, so here we are looking for the domain and the range of each relation, and they want us to write it in interval notation. Remember, domain are your x values. So what we're looking at on the graph is really where are the x values on the graph? How far out does it go? And so if we look at our x-axis here, this graph goes out to -2 and up to 2. So this is where our x values stop and start. So they start and stop right here, -2 to 2. And because we include those values, we're going to put brackets around it for our interval notation, and it would be -2 to 2. Remember, if it didn't include the number or it was infinity, we would use parentheses. All right, then our range. Look at your y values. This graph, it goes between 3 and -3. So our range, again, we're including the -3 because it's included on there, would be -3 to +3, and we would put brackets around it because it includes those numbers. All right, for B, if we look at our x values, the graph starts there. So it would go from -3, and then on the x-axis, it goes all the way out to 3. So that would be our domain. Our range, let's see, it is, here is our y values. Looks like it goes down to -1 and up to +1. All right, C, because they have the arrows on here, this means that this graph is going to continue on forever, going up and out. So when we're looking at our domain, since it's going to keep going out like this, it's going to keep going along that x-axis. So here's an x value. They're always going to have x values. So for the domain for this one, it's going to go on forever on the left and forever on the right. Your domain is going to be -infinity to +infinity. And remember, with infinity, we always put parentheses around it because it's not an actual value. Now, your range, if we look at our y values, okay, so we're looking at the y-axis here. My y values start at 0. There aren't any negatives included, but then because it goes on forever and it's going to keep going up, my range will be 0, and we'll put brackets there because it is included, and it'll go to +infinity because it goes on forever. So again, it would be a bracket around your 0 and then infinity and parentheses. All right, for D, we have our domain. We're looking at our x values, and again, with this one, it's kind of hard to visualize, but because we have those arrows, and this is a parabola, it's going to keep going and getting larger and larger. So it's going to keep going out. So it will eventually span the entire x-axis. So our domain is going to be -infinity to +infinity. Now our range, if we look at the y values, it starts here at 2, but then it goes down, and it'll keep going down through -infinity. So we're going to put -infinity to +2, but it won't go, the graph doesn't go any higher than 2. So the x or the y values up here will not be included. All right, and our last two where we're going to write the domain and the range. For E, we have a line here. And again, we have the arrows on, and so that means it's going to extend out forever in both directions. So if we look along our x-axis, it's always going to continue along that x-axis and have x values. So our domain for the line will be negative infinity to positive infinity. And then our range, it really doesn't have a limit on the y values either, because it's always going to keep going up and down. So it'll have an x and a y value. So our range is the same. It is negative infinity to infinity. For f, it's a wave, but if you look, it's going to keep going out and down and up and out. So the domain and range will be the same as E, just like our line. The domain will be negative infinity to positive infinity, and the range will be negative infinity to infinity. All right, here what we are doing is we are finding the domain of a function. And remember, your domain is your x values, or all the values for which the function is defined. So when we're defining a domain of a function, there are basically two things we have to worry about. One, if we have a fraction, remember in our denominator we can never have the value of 0. So we have to look for the numbers that will make x or the variables equal to 0. That would make our function undefined. And then also if you have a radical, we can't have a negative underneath an even-powered radical. So we have to look for those values as well. And that would make our domain undefined or our function undefined. So what you're going to do if they ask you to find the domain of each function. For the first one, okay, we have a fraction here. We are never concerned with the numerator when we're finding the domain. I don't care what's in there. It could have x plus 7. We don't worry about it. We're only worried about the denominator because this is where, we could get a 0 in our denominator and make it undefined. So to find out what value of x will make the denominator undefined, you take whatever's on the bottom, so in this case x minus 2, and you set it equal to 0, and then we're going to solve the equation. So this one's nice and simple. We'll add 2 to both sides, and I get x equals 2. So our domain is any number except x equals 2, because if x equals 2, it will give me a 0 in my denominator, which isn't allowed. So if we were to write the domain, and they're sometimes going to ask for it in set builder notation, which is where we put the brackets, and we do x, straight line x, which stands for the set of all x. The straight line means such that x is an element of real numbers, but x cannot equal 2. So it's basically saying it's every number except for 2. With b, again, we have a fraction. I am not concerned because I'm finding the domain with the numerator. The numerator can be 0, so that's not a worry. It's only the denominator I'm worried about because it can't be 0. So we'll take our 16x plus 5 and make that equal to 0 and solve. So we'll subtract 5 from both sides. And we get 16x equals negative 5. Divide by 16. So x equals negative 5/16. And so again, my domain is all real numbers except x cannot equal negative 5/16 because that will give me a 0 in my denominator. So if we write it in set builder notation, it would be a set of all x such that x is an element of real numbers, but x cannot equal negative 5/16. And that is it for that one. All right, for C and D, we have radicals. And recall, with radicals, we can't have a negative number underneath the radical. So what we're going to do is you're going to take the equation under the radical, 3x minus 2, and we need to solve it so that x is always either 0 or a positive number. So this equation or we'll call it an inequality now, must be greater than or equal to 0. And then we solve it like we would a regular equation. We add 2 to both sides. So we get 3x is greater than or equal to 2. Divide by 3. So here, our domain is x must be greater than or equal to 2/3. So our domain is any real numbers where x is greater or equal than or equal to 2/3. All right, for D, same thing. It's under the radical. It's even numbers. So we're going to take 10 minus 19x and set it so that it is greater than or equal to 0. We will subtract 10 from both sides. So we get negative 19x is greater than or equal to negative 10. Divide by negative 19. 2 negatives are going to make a positive, so x is, and again, because we're dividing by a negative here, remember your rules for solving inequalities, you got to flip your inequality sign. So x is less than or equal to 10/19. So in this case, x will have to be less than or equal to 10/19 in order for it to make it a positive value under the radical. So our domain would be anything less than or equal to 10/19. We have 2 more where we have to find the domain of the function. Now h, or e, where we're looking at h of x, is going to be kind of like a double whammy here, because not only do we have a fraction, but we have a radical underneath. So this time we can't have a 0 in our denominator, and we also can't have a negative number underneath the radical. So when we solve this one, we're going to take the value under the radical, because that's in my denominator, so 7x plus 4. And this time it has to be greater than 0. It can't be greater than or equal to, because we can't have 0 underneath the radical, or underneath the denominator. So to solve it, we will subtract 4 from both sides. So we get 7x is greater than negative 4. Divide by 7. So x is greater than negative 4/7. So our domain is any value that's greater than negative 4/7. And our last one here, we have p of x is equal to x squared minus 3x plus 2. Now when we're looking at our domain here, we don't have a fraction, so I don't have to worry about a 0 in my denominator, and we don't have a radical. So for this problem, our domain is all real numbers, because I don't have any of those special cases. So I can plug in any value for x and get an answer that will make sense or that will work. So again, it's all real numbers. I don't have to worry about any special cases there. There's no fraction to worry about a 0 in my denominator, and no even numbered radical to worry about a negative number underneath the radical. All right, so here we are going to look at graphing functions, and they give us a table of values, and they ask us to graph it. So remember, f of x is just like having y. So we have x values here, which is what we're going to plug into our equation and solve it to find f of x or y, and then we'll plot our ordered pairs. So our first value is negative 2. So really we're finding f of negative 2, and that will be equal to 2 times negative 2 plus 1. So 2 times negative 2 will give me negative 4 plus 1, which equals a negative 3. So I'll put that negative 3 up there. So when I plot my ordered pair is going to be negative 2, negative 3. When I plug in negative 1, we'll do 2 times negative 1 plus 1 2 times negative 1 is negative 2, plus a positive 1 will give me negative 1. So my ordered pair would be negative 1, negative 1. Plug in 0, we'll do 2 times 0 plus 1. Anything times 0 is 0, so 0 plus 1 is 1. 2 times 1 plus 1 will give me 2 plus 1, or 3. And then we do 2 times 2 plus 1, so 4 plus 1 equals 5. So I'm going to plot my ordered pairs. We'll have negative 2, 3. So again, start on the x-axis, go out to negative 2. Then we'll go down to negative 3. So my point will be right here. Then we have negative 1, negative 1. So out to negative 1 on the x-axis, down to negative 1 on the y. We have 0, 1. So we'll go to 0 on the x-axis, up to 1 on the y. 1, 3. So out to 1 on the x, up to 3 on the y. And then 2, 5 will be right here. And we will draw our line. So we've graphed our function. Now to check it on your calculator, if you have a graphing calculator, I'm using the TI-84 Plus. The TI-83 works. TI-84 is what I'm familiar with, or the Texas Instruments calculators. So to do that, at the top, underneath the viewing window, you have the graphing button. So you would press y equals, and then you would enter in your equation 2x plus 1. So you would do 2. The x, or the variable button, if you look at your calculator, you have a green alpha button, which is up near the top. Right next to it is a button that says, and I'll put it on here, it has x, t, theta, and n. This is your variable button. So you would press this for x, and then do plus 1. And then to graph it, you hit the graph button, which is all the way opposite the y equals button. If your graph doesn't look like the one here, this should be with your standard screen, what you need to do is go to the zoom button, which is the middle of the graph buttons, hit zoom 6, because that'll put you on your standard window, and that should allow you to see your graph. All right, so now we're going to graph x squared minus 3. And again, they give us some x values. We have to find the y values, or g of x. So our first value is negative 2. So we will do g of negative 2, which means we'll do negative 2 squared minus 3, or 4 minus 3, and we get 1. Next we have g of negative 1, which is the same as negative 1 squared minus 3. Negative 1 squared is 1. 1 minus 3 will give us a negative 2. Then we're going to do g of 0, which is 0 squared minus 3. Anything, or 0 squared is 0, so we have our negative 3 as our answer. G of 1 will be 1 squared minus 3. 1 squared is 1. 1 minus 3 will give me a negative 2. And we have also g of 2, which we're going to do 2 squared minus 3. 2 squared is 4. 4 minus 3 will give us 1. And when we go to plot our points, we have negative 2, 1. So I'll go out to negative 2 on the x-axis, up to 1. Then I have negative 1, negative 2. So that will be down there. 0, negative 3 will be right here. And then I have 1, negative 2, and 2, 1. And you're going to notice here that this, because it's an x squared graph, is going to be in the shape of a U, or it's called a parabola. Okay, so that is our function there. And again, you can check it on your calculator. All right, so here we are looking at our function of h of x equals the square root of x minus 1, and they give us x values. We have to find the y, or h of x. So first, what we're going to do is do h of 1, which is going to be the square root of 1 minus 1, or the square root of 0. The square root of 0 is 0. For 2, we have h of 2. So we are going to do the square root of 2 minus 1, which will give me the square root of 1, which is 1. Then we're going to do h of 5, which will be the square root of 5 minus 1, which will give me the square root of 4, which is 2. And last, we have h of 10, which will be 10 minus 1, which gives me the square root of 9, which equals 3. And then we'll graph it. So we will have 1, 0. We'll go right there. 2, 1 goes here. 5, 2, and then we have 10, which is all the way out here, 3. And this is your graph of a radical. It's kind of like half of a parabola. Okay, here we are graphing the absolute value of x plus 3. So when we evaluate, we'll do j of negative 2 first. So we have j of negative 2, and it will be, remember, absolute value. When you evaluate it, those two straight lines mean absolute value. It's the distance the number is from 0. So the absolute value of negative 2 is positive 2. It's 2 spaces away, and 2 plus 3 will give me 5. J of negative 1 will be the absolute value of negative 1 plus 3. The absolute value of negative 1 is 1. 1 plus 3 gives me 4. All right, J of 0 will be the absolute value of 0 plus 3. Well, 0 is 0 spaces away from 0, so it would be 0 plus 3, or 3. The J of 1 will be, let me erase that part. The absolute value of 1 plus 3, and 1 is 1 space away, so it will be 1 plus 3, which would give us 4. And then j of 2 will be the absolute value of 2 plus 3, which will give us 5, because the absolute value of 2 is 2, and 2 plus 3 will give us 5. So then we'll plot our points. So we go out to negative 2, up to 5, out to negative 1, up to 4, 0, 3 will be right there, 1, 4 will be here, and 2, 5 will be up here. And if you recall from when we were looking at the vertical line test, we had a graph that was in this shape. It's a V shape. That's your absolute value graph. Okay, for these examples, they ask you to give a rough sketch of the graph for each function using a graphing device, which basically means you're going to use a graphing calculator, and you can find them online, so you can Google graphing calculators to find one to use. So we're going to enter in the first one, negative x squared plus x. So again, on a Texas Instruments graphing calculator, at the top, you're going to press the y equals button. You're going to do negative, which is right down next to the enter button, x, which again is next to the alpha button, and then to square it, if you look below the alpha button, the third button down is the x squared button. If you press that, it'll square it. And then do plus x again and hit your graph. And you should have that standard window. And again, if you don't, press zoom 6 and it will give you the standard window. And when you look at your graph, it should look, and again, I'm doing a rough sketch here, so it's not going to be perfect. but something like this. So when you sketch it, it should look like that. It might be, I think mine's over a little bit. Let me erase this part a little bit. It should be more up like this. There we go. It's a parabola shape. You'll be able to see it on your calculator. All right, now for B, we're going to go back to our y equals. Now to do x to the third power, you're going to do x, and then below the clear button is what I call the caret. You'll press that, it's like a little up arrow, and then type in your 3, and then hit +1, and hit graph. And your graph should look like this. It should kind of be, have two little bends to it. Okay. All right, next we need to do 1 divided by x. So I'm going to put parentheses around it. I'm going to do parentheses 1, then divided by key and x, and close my parentheses. Excuse me. And graph it. All right, and this graph looks like this. So it's going to kind of ride the x and the y axis on both sides there and look like that. And then our last one will be the square root. To get the square root, you're going to do the blue second button, and the x squared button, because you'll see the radical above it. And then underneath your radical, sometimes it'll give you parentheses, sometimes it'll just give you under the radical. Depends on the age of your calculator. And we'll do 5 minus x under the radical. Sometimes you have to put parentheses, sometimes you don't. And graph it. And your graph should look like this. It should start at 5 and go out and up. And those are the graphed ones. You know, if you need extra help with the graphing, let me know. There are lots of good videos on using a graphing calculator if you need help with that. Or if you don't have a graphing calculator, like I said before, there are online versions of graphing calculators you can use. Now, when you go to take your final in the test center, you will need a graphing calculator. You can, though, borrow it from the library. So if you go to the library and take your student ID, you're allowed to borrow it for 4 hours, and you can take it to the test center and use it, and then take it back. All right, here we are performing operations on functions. So what we're doing here is we're either going to add, subtract, multiply, or divide with functions. So the first one, they give us two functions. We have f of x and g of x. And they ask us to first add the two functions together. So it's f plus g of x. All we're going to do here for f plus g of x is we are going to add the two functions together. So we'll take 3x minus 1 plus 5x plus 6. And here, because we're adding them, really it's like combining like terms. So we'll do 3x plus 5x, which gives us 8x. And then -1 plus +6 will give me 5. So that is my final answer when I add the two together. Now next, they ask for f times g of x. So we have f of g, or f times g of x, means that we are going to do 3x minus 1 times 5x plus 6. And when we multiply, we'll FOIL, so we will get 15x squared plus 18x, then -1 times 5, so minus 5x, and -1 times 6 minus 6. And then we combine our like terms, so we have 15x squared plus 18 minus 5 will give me 13x minus 6, and that's our final answer there. For B, what we're going to do here is first we want to do g minus f of x. So g comes first. So we are going to do, so this is g minus f of x. So it will be, we'll do x squared plus 2x minus 2x squared minus x plus 4. Now with subtraction, you do have to remember, you have that negative outside the parentheses here. So this negative right here outside this set of parentheses. It's like you have a negative 1 there. So you do have to distribute that negative 1 to everything on the inside. Basically, it means take the opposite of everything. So when I do that, I'm going to be left with my first expression, the x squared plus 2x will stay. But then negative 1 times 2x squared will give me negative 2x squared. A negative 1 times a negative x will give me positive x. A negative 1 times a positive 4 will give me negative 4. And then we're going to combine our like terms. So we have x squared minus 2x squared, which will give me negative x squared, or 1x squared. 2x plus x will give me plus 3x, and then minus 4. So that will be our final answer there. Our last operation that we're going to do here on this slide is f divided by g of x. So for f divided by g of x, we're going to start off, f will go on top, so we'll have 2x squared minus x plus 4 over x squared plus 2x. And what you want to do here is you want to see if you can simplify this at all by factoring. Let's see, on the bottom, I know it will factor, we can factor out an x, so it becomes x plus 2, and then let's see about the top. If we box it, just to practice that, so I do the box factoring, we put 2x squared here, and 4 here. Our middle term is a negative 1x, and we need to multiply to get, if we do 2 times 4, it gives us 8. So what we can multiply to get to 8, that will also give us a negative 1 if we use 2 negative signs. So our multiples of 8 are 2 and 4, 1 and 8. None of those, if we use 2 negatives, will give us that negative 1. So this is a prime factor, so we really can't do anything with it. So this will be our final answer. We can't do anything, and you could even leave the x squared plus 2x on the bottom. But you do want to check to see if you can factor it, and we can't, so we're done. All right, now here, we are going to add the two functions together, but we're going to do f plus g of 3. So then we're going to evaluate it for 3. So we're going to start off, and what I'm going to do for f plus g of 3 is I'm going to take my f function of 1 over x, and it will be plus my g function 1 over x squared, and I'm going to plug in our values. So we're going to do 1 over 3 plus, and we're going to plug in 3 here, 1 over 3 squared, or it's going to equal 9. So I'm going to go ahead and erase the 3 squared and put my 9 in there. Okay. Now I need to just add them together, do the math. So we need a common denominator, which will be 9. So I need to multiply this by 3 and this by 3 to get it to 9. So we'll have 3/9 plus 1/9, which gives me 4/9. And that's our final answer there. Now, for the next one, we have g divided by f of 4. So we have 1 over x squared divided by 1 over x, and we're going to plug in 4. So we'll do 4 squared is 16. So we'll have 1/16 divided by 1/4. fourth. And here, it's just one big division problem, so I'm going to write it out like we're used to seeing it. We'll do 1/16 divided by 1/4. And remember, with fractions, we don't actually divide fractions. We do what we call multiplying by the reciprocal. So when we do that, we keep the first fraction the same. So we keep 1/16. It's called our keep, or K. You change, or C, the division to multiplication. And you flip or take the reciprocal of the second fraction. So you flip the numerator and denominator. So we'll do times 4 over 1. And multiply straight across. 1 times 4 is 4. 16 times 1 is 16. So we get 4/16, but that simplifies to 1/4. So G divided by F of 4 equals 1/4. All right, next we're going to look at composite functions. Composite functions is when you evaluate a function at another function. This is red, A is red, F composed with G of X. So really what you're going to do is, since F is first, you're going to take the F function, which is, in our case, 2x squared plus 1, and it's F composed with G. So where there is a variable in F, you're going to plug in the second one, so G. So we're really going to have 2 times, and instead of x, I'm going to put my g function, so 5 minus x, and we'll keep the squared, and then plus 1. And now what we have to do is simplify it. So here, again, we're squaring this entire expression. So we'll have 2 times 5 minus x times 5 minus x plus 1. Again, I'm going to distribute the 2 to the first set of parentheses, so we'll have 10 minus 2x times 5 minus x plus 1. And we'll go ahead and FOIL. 10 times 5 is 50. 10 times x will give me negative 10x. We get negative 10x again, and then plus 2x squared plus 1. So when we simplify it, we get 50 minus 20x plus 2x squared plus 1. So now I'm going to add the 1 to the 50, which will give me 51, and I'm going to put it in descending order. So we'll do 2x squared minus 20x plus 51 for my final answer. Okay. For the next one, it is G composed with F. So I'm going to start with G, which is my 5 minus x, but where there's the x, I'm going to plug in F. So it's really going to be 5 minus, and then because x is a problem, we're going to put parentheses, 2x squared plus 1. And what we have to do here, remember that negative outside the parentheses means it's a negative 1, and you have to distribute it on the inside. So it will be 5 minus 2x squared minus 1, which will simplify to negative 2x squared, and it will be 5 minus 1, so plus 4. And that's our final answer. All right, for C, it's F composed with F, which is going to seem kind of crazy. But we're going to start off with our 2x squared plus 1. And then where there's a variable, we're going to plug in F again. So it's going to be 2. And instead of x squared, we're going to put in the parentheses 2x squared plus 1 squared plus 1. And then we'll, again, FOIL. So we'll have 2x squared plus 1 times 2x squared plus 1 plus 1. And we'll distribute. So we get, for the first one, 4x squared plus 2. And then we'll keep our rest of our problem and go ahead and FOIL. So 4x squared times 2x squared gives me 8x to the 4th. 4x squared times 1 will give me plus 4x squared. 2 times 2x squared will give me 4x squared. And then 2 times 1 will be plus 2, and then we have our plus 1 there. So combine your like terms, and you get 8x to the 4th power plus 8x squared plus 3. And that is your final answer. Okay, here we have two new functions. We have f of x equals the cubed root of x minus 1. Let's do that. And so that's right there. And then g of x equals x cubed plus 1. So the first thing we're going to do is f composed with g. So we're going to start off with our x, or our f, which is x minus 1. But instead of x, I'm going to plug in g. So I'm really going to have x cubed plus 1, which is our g, minus 1. And we'll do all the work to simplify this under the radical first. If we have plus 1 and minus 1, it's going to equal 0. So I'm going to end up right now with the cubed root of x cubed, because my 1's will equal 0. And then the cubed root of x cubed is equal to x. So that's my final answer there. Then we're going to do g composed with f. So g is x cubed plus 1. So what we have here is instead of x cubed, I'm going to plug in f. So I'm going to really have the cubed root of x minus 1 cubed, because it was x cubed. So I put this in for x and then cubed it, plus 1. If you have the cubed root and you cube it, remember from our radicals that you get what's under the radical. So we have x minus 1 plus 1, which will leave us with x in the end. Okay, so here we're going to do f composed with g of x first. So f is 1 over x. So we're going to do 1 over, and instead of x on the bottom, we're going to put in g. So it'll be 1 over x plus 2. So we got, again, that crazy complex fraction. But we can simplify this by simply doing 1 divided by 1 over x plus 2. Or remember, if we talked about dividing fractions, keep the first fraction the same. So 1 times, and do your reciprocal, x plus 2. It's over 1, but we don't really necessarily need to put that 1 there. And we can put that over 1. So when we multiply it out, we get just x plus 2, because 1 times x plus 2 is x plus 2. 1 times 1 is 1. We don't need the 1 underneath. So there's our final answer. Now for g composed with f, we have 1 for g over, it's x plus 2, but instead of x, I'm going to do 1 over x, 1 over x plus 2. So again, it's like a division problem. We have 1 divided by, now this one, because it is an expression underneath, I think instead of dividing with our fractions here, we're going to clear our equation of variables. So we're going to multiply everything, because our denominator is x. We're going to multiply everything by x. And let me rewrite the problem so you can see it better. So I'm going to multiply the bottom by x and the top by x. And this will get rid of my denominator there. Because if I do 1 over x times x over 1, because that's the same thing there, we get x over x, which equals 1, because the same thing on the top and the bottom equals 1. So on the bottom, I'm going to have 1 plus 2 times x is 2x. And then on the top, 1 times x is x. And by doing that, we simplified it. I can't do any more. I can't simplify because this x right here is part of an expression. So you can't just cancel out your x's there. It has to be attached by multiplication to the entire thing, not with addition there. So we're done. Now, for the domain of the above composite functions, for A, because we have no fraction to worry about, our domain is all real numbers. But for the second one, we have this fraction, and remember, your denominator can never equal 0. So the domain for that one, we will take to find it and set our denominator equal to 0 and solve. So we get 2x equals -1 divided by 2. So it's all real numbers except x cannot equal -1/2. So now we're looking at inverse functions. And the inverse of a function is really when you switch your domain in a range of two functions. To show that a function is an inverse of another, you would use the notation f of -1 of x, or whatever your variable is for your function. But the inverse is that -1 up there in the corner. It's not an exponent, it's just noting that it's an inverse. If you have a set of ordered pairs, it's easy to see if they are an inverse of each other because you'll take and switch your domain and range, which remember is your x and y values. So for the first one, f of x, we have 2, 1, and then g of x is 1, 2, so they switched the 2. For the second ordered pair, it's 5, -3, and then they did -3, 5, and then 6, 8 turned into 8, 6. So because they switched the ordered pairs, the x and the y values, this is an inverse of each other, and we just checked by looking at they switch the domain and the range. Now, for B, we have two functions where they give us the equations, and we have to show if they are inverses or not. The way to do that is to do the composition of both functions, and if you simplify them, you will get x each time. So what we're looking at is we're going to first do f composed with g of x, and then we're also going to do g composed with f of x. And once we do those, if they both simplify down to just a single x, that means that they are inverses of each other. So f of x is x plus 5, but if I'm going to do f composed with g, instead of my x there, I'm going to plug in x minus 5. So the first one, I will have x minus 5 plus 5. And if I simplify that, my 5's -5 plus 5 equals 0, so I'm left with just x. So that works. And then we have g composed with f of x. So I'll start with my x, but again, instead of x, I'm going to plug in f. So I'll do x plus 5 minus 5, which when I simplify that will leave me with x. So that is my final answer, and they are inverses because they both simplify to x. Okay, so here we're going to see if these are inverses as well, or show that they are inverses. So we're going to start off again. I will do the composite of f composed with g of x, and then also g composed of f of x. So if we start the first one, f is the 5th root of 3x minus 1, but I'm going to do the 3, and then instead of x, I'm going to plug in g, so I'll have x to the 5th power plus 1 divided by 3 minus 1. Now here, when we go to simplify, we're under the 5th root, but if I have 3 over 1 times this expression over 3, those 3's are going to cancel out. It will leave me with x to the 5th power plus 1 and then minus 1. X plus 1 and minus 1 equals 0, so I'm left with the 5th root of x to the 5th, which we know that if we divide 5 by 5, we get 1, so it equals x. So for that one, it works. Now we have to do g composed with f of x. So we're going to have g, let me draw a line there so we can have space. G is x to the 5th power plus 1 divided by 3. So instead of x to the 5th, I'm going to put f in there. So it will be the 5th root of, let erase this. Okay, so it's going to be the fifth root of 3x minus 1 raised to the fifth power plus 1 divided by 3. And if you recall, anytime we have the fifth root of something and we raise it to the fifth power, it gives us what's under the radical. So we'll get 3x minus 1 plus 1 over 3. Negative 1 plus positive 1 gives me 0, so we're left with 3x over 3. My 3's equal a 1, so my final answer is x. So they are inverses because we can simplify, do the composition of both, and get x for your answer. Let's take a look at D. So we're going to do f composed with g of x first. So f is x over x plus 1. So for the first one, instead of x, we're going to put the entire g. So we'll put x over 1 minus x over, and then we have x plus 1 here, so it's going to be x over 1 minus x, and then we have plus 1. So for this one, again, it's a complex fraction, and to clear our equation of these fractions, we're going to multiply by our common denominator. So we're going to multiply everything by 1 minus x. And if it helps, think of it like 1 minus x over 1. So we have 1 minus x over 1, and we're going to start multiplying. Okay, so what we are going to do is, up here on the top, it's nice because those will cancel and we get x. Now on the bottom, we have to multiply this entire problem by x minus 1 over 1. So for the first fraction, if you have x over 1 minus x times 1 minus x over 1, the 1 minus x's will cancel, and it leaves you with x plus, and then if you do 1 times 1 minus x, you get 1 minus x, which if we simplify, x plus 1 minus x will give me x on the top, and down on the bottom, the x's cancel, and I have 1, which is the same as x. So f composed of g of x equals x. And what I'm going to do is I will erase this side over here so I can do g composed with f of x. Give me a second to erase. Okay, so now let's do, from this problem here, we're going to do g composed of f of x. So g is x over x1 minus x. So we will have, for x, I'm going to plug in f, so it will be x over x plus 1 over 1 minus, and then we'll again plug in f, so it will be x over x plus 1. And again, to get rid of these complex fractions, we're going to multiply by our common denominator of x plus 1 over 1. And so we have x plus 1 over 1. So on the top there, our numerator and denominator will cancel out. It leaves us with x. Then on the bottom, 1 times x plus 1 is x plus 1. And when we do x over x plus 1 times, for the other one, x plus 1 over 1, remember the x plus 1's cancel and we get x. And this is, let me fix this, it will be x minus, or no, it's x plus 1 minus x. Okay. because we have the minus sign here. So this 1 became the x plus 1. And we put our minus, and then we simplified this. We got x. My x's, again, will cancel on the bottom. It leaves me with x over 1, which equals x. So they are inverses because you get x for both. Okay, so now we're going to find the inverse for a function. And if no inverse exists, we're going to show why it doesn't. To do this, to find the inverse of a function, first thing you're going to do is take your f of x and replace it with y. So we're going to make the equation y equals 3x plus 2. And then remember, inverse, you invert your x and your y. So you're going to change all your x and y variables. So I'm going to rewrite my equation as x equals 3y plus 2. And then the last thing you need to do is solve your equation for y. So now that it is y equals. So we will subtract 2 from both sides. So I get x minus 2 equals 3y. And then we'll divide everything by 3. So we get y equals x minus 2 over 3. And that's the inverse. And the last thing you want to do is replace that y with your inverse notation. So we'll do f of negative 1 of x equals x minus 2 over 3. All right, if we look at b, instead of g of x, we're going to do y equals the cubed root of 7 minus 5x. And then we'll switch our variables. So it will become x equals the cubed root of 7 minus 5y. And to solve for y here, the first thing we need to do is go ahead and cube both sides. So we get rid of that cubed root. So now I have x cubed is equal to 7 minus 5y. And we will subtract 7 from both sides. So I get x cubed minus 7 equals negative 5y. Divide everything by negative 5. So g of negative 1 of x, or y, equals x cubed minus 7 over negative 5. All right, let's keep going and look at q of x. And again, we're going to make it y equals 2x over x minus 3. And then we'll switch our x and y's. So it becomes x equals 2y over y minus 3. And the first thing I want to do is get rid of that denominator. So I'm going to multiply both sides by x minus 3. So I will have, or y minus 3. So I will have x times y minus 3 is equal to 2y over y minus 3 times y minus 3 over 1. And what happens there is the y minus 3's cancel out there, so we're left with 2y is equal to, when I distribute here, we get xy minus 3x. And then we divide by 2. And that is going to leave us with, actually, before we divide by 2, because we have that y there, and we're solving for y. So after I distributed, I have minus xy. So what I want to do is I want to move that over to where the y is, because we're solving for y. So right now, this is what I have. I have negative 3x equals 2y minus xy. And we are going to factor out a y here. So when we do that on this side, I'm going to write it over here, we're going to get negative 3x is equal to y times, if I divide this by y and this by y, it's going to leave me with 2 minus x. And now we'll divide both sides by 2 minus x. And it will give me, they will cancel out. So my inverse will be q of negative 1 of x is equal to this right here. So negative 3x over 2 minus x. And I know I made kind of a mess of that, so go ahead and record that. So what I'm going to do is do a little bit of erasing here so we can see the problem. And I will draw a line, and then I will erase a little bit here, and we'll do the problem up here so we can see it all. Okay, so we have x plus 1 over x plus 2, so we're going to make it y equals x plus 1 over x plus 2, and then we'll do x equals y plus 1 over y plus 2. And what we want to do here is first get rid of that denominator. So let's multiply everything by our denominator so we can eliminate it. And if we do something on one side, we have to do it to the other. So that's going to give me xy plus 2x is equal to y plus 1. And again, I am going to move my xy over to the other side. So I'll subtract xy. And it's going to leave me with 2x is equal to y plus 1 minus xy. And to help us out here, this is a lot of moving around. It's a difficult one. Let's subtract the 1, move it over here. So I end up with 2x minus 1 equals y minus xy. And the reason I did that is because now I can factor this. And I can have 2x minus 1 equals, and I can pull out a y. So it'll be y times 1 minus x. And then to get y by itself, we'll divide by 1 minus x. And so p of negative 1 of x equals, it's going to be kind of hard to see, but it's 2x minus 1 over 1 minus x. So there's our final answer. 2x minus 1 over 1 minus x. Okay, our last two examples for this module. So again, we're finding the inverse. So I'm going to make this y equals x squared plus 2. And then I'm going to flip my x and my y. So it's going to be x equals y squared plus 2. And I want to solve for y, so I'll subtract 2 from both sides. And I get x minus 2 equals y squared. But I want y, so I'm going to have to take the square root of both sides. So my final answer will be x minus 2, the square root of x minus 2 equals y, or t of negative 1 of x is going to equal the square root of x minus 2, because I can't do anything with that. So that's done. And now our last one, for this one, we can make it y equals x to the 5th minus 5x cubed minus 1 and switch our x and y's. But to solve it, we would need to be able to factor. And because this is not factorable, there is no inverse. So the inverse here does not exist because you can't factor it. So DNE stands for does not exist because we can't factor the expression. And that's it.